Good afternoon, everyone. My name is Zhang, and I'm from Wuhan University, China. My talk will be a new real-time ZTD grid product over China and applications in PVP. My presentation includes 4 sections. They are introduction, data and processing strategy, real-time ZTD grid product, and followed by the section summary and conclusions. As we know, the signal transmitting from the satellite to the ground receiver will be delayed by the troposphere. In GNSS data processing, we generally map the slant delays into the zenith direction, which we call ZTD. And ZTD can be divided into 2 parts, the hydrostatic part, ZHD, and the non-hydrostatic part, ZWD. ZHD can be precisely modeled, but for ZWD, due to the complex variations of water vapor, it can be harder to be precisely modeled. Why we need ZTD in real time? We can use them to support meteorological nowcasting. We can also use them in navigation, and we can also use them in real-time PV applications, which we will focus on in our study. In PVP, ZTD and the vertical position are strongly correlated, which will partly results in the relatively longer convergence time compared to other techniques like RTK. But if we can get a priori ZTD with high accuracy in advance, then we can fix them or strongly constrain them in the PP processing, which will, of course, accelerate the convergence. How about the performances of current commonly used real-time ZTD models or products? For empirical models like Sastamonian, Hopfield, and the later UMB models and the Ignos model, and the most recent models derived from meteorological reanalysis, they can provide ZTD with accuracy generally not better than 4 centimeters. And there are also a lot of study focusing on generating real-time ZTD product based on cost networks. They can provide ZTD with accuracy better than 2 centimeters, but most of the study are generally at a scale of several hundreds of kilometers. So in our study, our objective is to develop a ZTD grid product in real time with high accuracy at the national scale of China and easy to use. And our solution will be to combine an empirical ZTD vertical correction model based on reanalysis and the ZTD, real-time ZTD solutions from real-time GNSS stations. The reanalysis we used here is EIA interim from ECMWF with time resolution of 6 hours and horizontal resolution of 0.75 degrees with 37 pressure levels covering 4 years. The ZTD at a specific location from reanalysis can be divided into 2 parts. The first one is the part above the top level, and the second one is the part between the location altitude and the top level. The first part can be estimated by Sastamonian model, and the second one can be calculated by integration of reflectivity. Of course, we need to consider the altitude difference between the user location and the bottom level. This table summarizes the ZTD errors from reanalysis compared to IGS final ZTD products in 1 year at 6 stations in China. And we can find the mean RMS of ZTD errors is about 1.4 centimeters. The GNSS data we used in our study mainly comes from 2 networks, the CMO NOC network and NBUS network. About 253 stations in CMO NOC network, as denoted as green circles in this figure, will be used for product generation. The other 16 stations denoted as red circles will be used for product evaluations. And about 95 NBUS stations will be used for PPP tests. This table gives a GNSS data processing strategy. The data are in 30 seconds and were processed by Panda software in simulated real-time PVP, which means the data are read from files instead of real-time data stream. The IGS archived real-time products will be used. This table gives the bells and RMS of real-time ZTD arrows at all CMO stations in 4 months in 4 months in 2015. And we can find the mean bells and RMS is about 0.25 and 1.18 centimeters respectively. As mentioned before, before we generate the real-time ZTD grid product, we need to develop a ZTD vertical correction model first. And this figure gives ZTD profiles at 3 stations from reanalysis. And we can find the ZTD roughly changes exponentially with altitude. So we decide to use this equation to fit the ZTD profiles. But instead of fit the whole ZTD profiles, we considering the actual commonly used situation, we will only fit the ZTD within 3 kilometers from the ground surface. This is a typo here. It's surface, not surface. But anyway, we can find the STD of the fitting residual RMS reduced from 1.7 centimeters to 0.4 centimeters. After getting beta time series of 4 years at each grid point, we analyzed the beta in both domain and the temporal, in both spatial and temporal domains. And we can find significant variations of beta in spatial. And the main periodical cycles in the beta time series are annual and semi-annual cycles. So we use this equation to fit the time series at each grid point. And finally, we can get a table, coefficients table for each grid point. And according to our sensitivity test, the fitting residual RMS is about corresponds to 1 centimeter ZTD. After we get in the vertical correction model, we can start to generate the real-time ZTD grid product. Given the area roughly covering China with a resolution of 0.75 degrees, we search GNSS stations within 1,000 kilometers within around each grid point. And assuming we find N stations, then we will use the ZTD vertical correction model to convert ZTD from the station altitudes to the grid surface altitudes. And then we use IDW method to calculate the average value as ZTD at the grid point. And finally, we use the vertical correction model again to convert the ZTD to mean sea level and broadcast to users. At the user side, we receive the real-time ZTD grid product and use the vertical correction model to convert the ZTD from the grid from the mean sea level to the user location, and then calculate the average as the ZTD at the user side. So next, we can use the 16 CMOC stations as test station to assess the ZTD grid product accuracy. And these 16 stations locate in regions with significant different latitude, longitude, and altitude. This table gives the ZTD, real-time ZTD arrows from the grid product compared to the post-processed final ZTD solutions in 4 months. And we can find the mean RMS of the ZTD is about 1.56 centimeters. The bottom left figure gives the bells and RMS at the individual station. And we can find there are no significant differences among stations in different regions. And this figure gives the comparison by using our grid product with other commonly used empirical models. And we can also find significant improvements by using our product, as indicated by the red lines. Finally, we do PB convergence tests at 95 NBAS stations. The data covers period of 1 week in 2016. This figure gives PB convergence comparisons. The left two panels are results for BDS PPP, and the right two panels are results for GPS PPP. The top two levels are results in horizontal component, and the bottom are for results in vertical component. And we can find at the same moment the position errors significantly reduced by using our grid product, as shown by the black line and the green line. And this table summarizes the convergence time given the thresholds of 0.2 meter in horizontal and 0.5 meter in vertical component. And we can also find the convergence time significantly reduced by using our grid product, especially in the vertical component. Okay, so comes to the summary and the conclusions. In our study, we developed a real-time CTD grid product over China. It combines empirical CTD vertical correction model and real-time GNSS network. It has high accuracy. It can be used in real time. It's high resolution and at the national scale of China and easy to use. By using the grid product, it can significantly accelerate PPP convergences, especially in the vertical component. And it can be easily expanded to a larger scale when more and more real-time stations are available. Okay, that's all. Thank you.